Material Science and Engineering on mixed oxide catalyst for epoxidation from a room temperature aerosol process. And the speaker is Greg Pukarski.
Thanks. This talk's also about Solgel kind of processes, I guess, alkoxide, metal alkoxide processes to make catalysts. It's a little bit different than the previous talk in that we're producing all the materials in one step, so we aren't mixing in different powders or synthesizing nanoparticles. That's the goal. And one of the interests that we have is to demonstrate the relationship between nanostructure and catalytic activity in a fairly simple reaction. Let's see, this guy is too big for this. Aerosol processes versus solution processes have several advantages. In particular, for the process I'm going to talk about, there's no solvent involved. We're dealing with vapor phase mixing of components and reactions to form metal oxides, mixed oxides in this case. The reaction to make the catalyst is, the rate of that reaction is severely enhanced, okay, when it occurs in sub-micron size aerosol droplets, okay, over what happens in a beaker, partially by byproduct removal, which is rapid and small droplets, okay, due to enhanced vapor pressure in these droplets. And because the process happens so quickly from a vapor phase to a liquid phase to a solid phase in a matter of a few seconds, it's easy to get mixed oxides, and highly mixed oxides, where in this case we want to have a TiOSi mixture of two components that don't normally react together. So by mixing the vapors, throwing the things together, we can get a high content of these mixed oxide states that are catalytic. And this process is, that I'll show you, is cheap and fairly clean depending on how you do it. So, from a Solgel point of view, these are your options. Okay. Solution chemistry, and as applied in industry, things like precipitated silica or silica gel, solution with titania, okay, usually industrially involves sodium silicate. In the lab it involves TiOS or TMOS Solgel reactions, and you can make things like aerogels, kind of super ceramics. Okay, this is an aerogel that was made at Sandia, where I worked once. And it shows the thermal insulating behavior of these kind of low density silicates. The flame route is basically how you make carbon black, right? You make an aerosol with some carbon precursor and burn it, and you get soot out of that. You can do this with silica. You can do it with titanium. Okay, fumed silica, pyrolytic titanium is made that way. We have our process is a hybrid between these solution and pyrolytic routes. We make a vapor like in the pyrolytic ceramics, but the vapor is made of chemical reactants. We never heat it up. It's all done at room temperature basically, except you need a certain temperature to keep the reactants in the vapor phase. We mix the reactants, they condense into a cloud, basically like a cloud you see in the sky, and they rapidly form ceramic oxides. Okay, the advantage for catalysts, one advantage is that we can make mixed oxides because the vapors mix without worrying about miscibility. Okay, they co-condense if you play with the system right, and then you can get mixed oxides up here. Another advantage over solutions, this thing happens a lot faster. So this more or less shows that kind of business. And one system for making silica would be to do this with TiOS and Ethanol is a byproduct. There's no solvent to mix water and TiSi because you're just condensing vapors together. And HCl is a gas that's present as a catalyst in this. So these, if you don't know about Solgel, these are kind of some pictures of the reactions. Alkoxide and water, you hydrolyze, end up basically with SiO2 or TiO2. And these are the two systems that we're going to, so you have a hydrolysis and a condensation, you get with an oxide. And these two reactions are going to run simultaneously, throwing the vapors together in this case. Okay. If you did this in solution, it's difficult to get the two components to mix. It's possible, but more difficult than a vapor system. And in a solution, it requires co-solvents for the components. We aren't using solvents at all. Okay, so these are kind of schematics of two reactors that we've been using for a couple of years. This is a laminar flow system where we have the various vapor streams coming in, and they mix, and there's a diffusion between the vapor streams at the top. They're all continuous processes. Okay, and we can control the diffusion between the reactants to control the structure, and it's kind of a more or less an academic system. All right, when we really want to make a lot of powder, I guess we go to this kind of mixed feed system where we mix all this, we run the vapors into a mixing chamber, we mix them at high temperature, and then we have controlled temperatures along the route, we collect powders down here, which are our heterogeneous catalysts for these oxidation reactions. All right, so in this kind of system there's a variety, and it's basically the same slide, but this is how we've been looking at this recently. One problem is that most silica alkoxides react much slower than titania alkoxides. Okay, and this whole picture happens in about 5 seconds. It flows through this. Okay? So, because silica reacts slower, if you co-feed the two components here, you have a tendency to form titania first, and the silica doesn't form until later in the process. So it's possible to feed in silica first, begin its reaction, and then feed in titania at a later point. So there's an infinite number of varieties of this reactor that you can make. We've tried some of those. All the different components of the reactor can be run at different temperatures. We can cool the condensation chamber, for instance, to drive liquid phase condensation earlier. Okay, so I wanted to mention we use Smallangle X-ray scattering as a technique to characterize our particles, our nanoparticles that we get out of this reactor. Okay, so I wanted to give you a little hint about what Smallangle X-ray scattering is. It's basically a transmission diffraction experiment. Okay, and you're looking at small angles. Okay, and typically you plot the data as a log intensity versus log scattering angle. Okay, and this is a typical shape you'd see from this kind of material, because these materials will form aggregates of this type, okay, including the pyrolytic, the solution route, and these aerosol gel materials form kind of aggregates where the primary particles here would be on the order of 10 to 50 nanometer. Okay, and the total aggregate is something that can be up to like 0.1 micron. Okay.
Do you have a surface area?
Right, yeah, I do. I mean, the smallest particles would be like 700 meters squared per gram. And we can continuously produce this. Okay, so there's no problem with making quantities of this stuff. So it's equivalent to the aerogel thing I showed at the beginning, as far as surface. You can also, in a lot of applications, you want to have lower surface area. Okay, so in fact, we've tried in some cases to make lower surface area, like 10 meters squared per gram for some applications, like reinforcing fillers and that kind of thing. Okay, so anyway, this is the analytic technique we specialize in. So I want to show you this. The basic features, these primary particles show up as a knee in this curve, in this log-log curve, and the aggregates show up as another knee. In between, it shows you the slope in a log-log is a dimension. negative of the dimension of the object. So 3 would be kind of the highest number, a three-dimensional object. A linear object would have a slope of 1, and these will have slopes in between 3 and 1. In other words, they're less than three-dimensional, more than one-dimensional. Okay, 2 would be a random object. Okay, and that's all I want you to get out of this. We can get the surface area from these curves from the high end also. But basically, we're looking at the primary particle size, and aggregate size, and the dimension that describes how the things are put together. They're put together in different ways because of the growth mechanisms. Okay, and basically, you can look at the growth mechanisms of these kind of things in terms of if a primary comes in, does it stick immediately? If it sticks immediately, then you get an open structure with a lower dimension, closer to 1, closer to linear. If it comes in and doesn't stick immediately and can bounce around, you get a denser structure. So something like Tetris, if you ever played that. Okay. If reaction rate is governing reaction of the primary particle with the aggregate, you get denser. If transport is limiting and it reacts immediately, you get lower dimension objects. All right, so, and that business has been well worked out. So here's some surface areas from early work we did with a laminar flow reactor in producing silica with TiOS and TMOS. This is a methoxy with silica in the middle, and this is ethoxy with silica in the middle. TMOS is much more reactive and also produces methanol that will make you go blind. TiOS is a safer thing to use. Okay, so the issue here is that we can get completely different structures in these materials, and that's really the only thing I want you to look at here. The primary particle, in this case, is close to 50 nanometers, I guess, or let's see, 50 angstrom, 5 nanometers, this A, 0.1 inverse angstrom. All right, so this thing has a huge surface area which is accessible. Okay, this mass fractal kind of aggregated structure allows access to these surface areas. And this material would have kind of these intermediate, let's see, that material would have something like 300 meters squared per gram. Okay, we get higher than that. In fact, these primary particles can go off the scale in this plot. This is like 1 over the size, basically. That number minus this Q size here. Okay. So in solution, from solution routes using scattering, you can watch the growth of these mass fractal aggregates. Okay, so we start with a primary, something like a POS structure for silica. And you can watch these things grow with time. To watch this in solution, you more or less have to get core statistics in the scattering data from a lab source. And we have ways to fit these curves to get statistical analysis of the numbers of the particle sizes and that kind of business. Right. So using that kind of technique, we've mapped out this mixed phase reactor. So we basically understand how to control the growth of different kinds of structures, both by temperatures, residence times in different chambers, and also reactants that we include in this. Okay, and we're using mostly HCl. We've tried some other organic acids, like was mentioned earlier. Here's some micrographs of the variability in structure that you can get in a pure titania system under conditions where we're trying to get large-scale particles. So these are SEMs, and they're near a micron size, roughly, in most of these pictures. And this is a typical fit to one of these kind of structures where we have the primary particle size, 7 nanometer, aggregates roughly 10 times bigger than that, in a fairly high dimension, indicating that it's reaction limited process. So it's a denser structure because the particles bounce around and they pull in. The materials have fairly monodisperse pore sizes. Okay, they have IR curves from this kind of material. We're looking at some organic content, significant hydroxyl and water content, because water is one of the vapors in the materials. From these curves, you can also tell with a mixed oxide how there's a peak that's associated with the SiO-Ti bond. So you kind of quantify the amount of that. And the materials you get, the high surface area materials, have a temperature sensitivity. Okay? And in fairly mild conditions, you can see a decay in the specific surface area from this. This is pure silica produced in a laminar flow reactor. Right, so again, in making mixed oxides for catalysis, there's a huge range here. Even if you pick a mixed feed reactor, okay, you have all the temperatures of the different chambers, you have where you feed the reactants in, and then you can balance out the reactivity of the two components. We're making silica titania, so you can run silica tetrachloride in this, you can run TiOS, TMOS, as some other larger organic group, silicates. Usually you want to increase the reaction rate of silica, and these are the fastest. Okay, so, and then the titania, we're using TTIP mostly, but there's some other slower titanias that can be used, titania alkoxides. And this is more or less a list of, and then you have the flow rates of all the reactants to basically tune the content of titania in the mixed oxide. Okay. This is, we've done XPS and also ICP on these to determine basically the titania to silica ratio of the mixed oxides that we get out. Okay, so one way to look at the particle size that's reported in the literature of the titania domains in these mixed oxides is to look at the UV spectrum. Davis reported this kind of business where he's looking at different particle or different titania domain sizes, and you can tune this UV absorption curve by the titania domain size. And we've seen shifts in the UV absorption in our materials. We've tried to use this as a tunable UV absorbent also for an additive to polymers. Okay. You run into a few problems with that, including that as you tune the UV absorption, you tend to make the material catalytic, which is a negative feature. Okay. This is showing this business where you can observe a certain peak associated with TiO-Si, and that peak shows up in our patterns also, somewhere right here. Okay, so we're getting a pretty strong peak associated with that. All right, and from this kind of solution room temperature process, even though we're using aerosol, you get amorphous. This is the diffraction pattern intensity versus 2 theta, and it's an amorphous halo from this mostly silica material. Okay, so we ran these in two simple epoxidation reactions with organic alkenes and a peroxide, and then using this heterogeneous catalyst mixed in and basically stirring slurry of it. So it's a fairly simple operation. We didn't worry about presence of water or oxygen or anything else. We just did it. I mean, we had dry glassware, but basically in a little beaker on our lab bench, and nothing special going on. This schematic down here is just showing more or less what the literature view from Baker at ETH of what's going on with this epoxidation reaction in these mixed oxides. And the theme of this is that the TiO-Si bond is the thing that's doing the work. Okay, so the more isolated TIs you have in the materials, it's believed that at least as far as these kind of mechanisms, is going to lead to your epoxidation reaction from the alkene that enters right here. Okay. So we've done this with these powders. First, we did some styrene reactions. We had some conversion. Okay, and then lately we've been really looking at concentrating on epoxidation of cyclohexene with fuming hydroperoxide, and we've been looking at fairly in depth at this kind of business. Okay, so these are this kind of X-ray scattering curve. This data was taken at the EPS in Chicago, the Advanced Photon Source in Argonne National Lab. The reason to go there is that this size is a micron, this 0.0001, which you can't access in a lab instrument. Okay, and it also goes out, the range of a lab instrument is kind of right here, basically to the same endpoint. Okay, and the advantage of that is you can look at, these are decades in size. So there's 4 decades in size, going from an angstrom to a micron. Okay, 10,000 angstroms a micron. And you can march across that size scale and look at the reactivity of the catalyst. Okay, in this hexene, cyclohexene epoxidation reaction, the conversion isn't huge. Okay, but it's statistical. I mean, the error in this conversion from gas chromatography is something like 0.02 or something. I mean, it's pretty good, fairly good accuracy numbers, and we've repeated the reactions. Okay, so we get the particle sizes from these kind of fits to these curves that assume a mass fractal aggregated structure for a catalyst. And we get the primary particle, the aggregate size, and the dimension, which are reported as basically radii here. Okay. 3 nanometers. This is 75 nanometers. It's an angstrom here. The last catalyst has a very large particle size, and you get 0 reactivity. But all these have, by ICP, have about 20% titanium. Okay, so they're on the high end of our materials. And they were made with TMOS and TTIP. The fractal dimension has a range that's varying according to this kind of growth rate. And we've looked at that business. Okay, so the interesting thing is that, you know, this demonstration that this structure and the reactivity are directly related to each other. Okay. The other thing of interest is that we know that there's organics on these materials. Okay, and the organics are good in this case because they're going to make a hydrophobic surface to prevent water from contaminating the epoxidation reaction. Okay, so when you bake it at mild conditions, and this is baked at 140 degrees under vacuum for 24 hours, and nothing severe. Just still amorphous. The reactivity changes, and also the strange thing is that these sizes get smaller. And I showed you earlier that the surface area for the pure silica systems made with this laminar flow reaction got smaller as you baked it at mild conditions. In this case, the surface area increases basically. That's what this is saying. Okay, so you can think about these numbers comparing the unbaked and the baked is that the way we look at it is there's an organic groups at the surface that are enhancing the catalytic activity. Okay, so when you bake it at 140 for 24 hours, basically burn off some of those. Okay, which makes the particles smaller. It's not a high enough temperature to center the inorganics, but it's high enough to kill the organics. So the reactivity dies off because it's less hydrophobic on the surface, and that's basically the scheme here of what's going on. There's also a dimensionality change, which indicates some maybe reactivity in this kind of mild baking condition. So that's one of the few kind of summary slides. Okay, so we're looking at this as a highly versatile and clean reaction where we're reducing the consumption of, say, solvents that you need in a solution route. The versatility comes from the idea that in an aerosol you can force miscibility without solvents. Okay, vapors mix, and if you condense a vapor, you can co-condense things that don't normally co-condense. And also because there's such small droplets, the transport rate from the droplets into the droplets of reactants in and byproducts out can enhance the reaction rate by a factor of about 10. Okay, if you put these in a beaker and react them, like just pure silica, it could take a day to make a gel, okay, that you would dry and make a powder from. In this case, it's happening in kind of seconds. Okay, it's a continuous reaction, so we can just pump reactants in until we get sick of pumping reactants in and make as many as we want. It would seem that you could scale this up fairly easily. What else? It's running in ambient conditions, mostly. I mean, there's some heating involved as far as keeping the reactants in a vapor phase. We believe this is low cost, okay, compared to the conventional routes of making materials. The whole reactor can be made out of PVC plumbing. And the initial reactor was made out of plumbing pipes. Now we have more expensive components, but Okay, so I wanted to also mention two other things, two other slides in other words. One, this is one area where we're applying this kind of production of ceramic powders somewhere here. Okay, we're also making organically modified silica as a reinforcing filler for polymers. We've also been working with P&G on this kind of UV absorbent business. P&G is also involved in this work, some of the chemists at Miami Valley. And we've been doing this process where you can put a substrate into the stream and make anti-reflective coatings, okay, for plastics and for metals. The coatings for metals aren't for optical properties. So that's pretty much what's going on here. The support for this work is mostly from NSF. There's a stream of grants. The original grant didn't really have much to do with this, but the later grants have been going in the direction of developing this technology. And also P&G has supported us in part through collaboration, also Goodyear for the elastomer reinforcement part of this. So that's the whole story here. Thanks for your attention.
What would be the difference of comparing the stabilities, thermal or moisture sensitivity of your materials to those made in conventional methods, say the titanium silica?
The TS1 catalyst, I guess, would be the current catalyst of interest, I guess, in the industry. The reaction we're testing this with, the thermal stability isn't good. I mean, these nano-structured particles, and these are really nano, I mean, in other words, less than 10 nanometers, tend to center at very low temperatures. And I tried to show that in the early slide, that even if you go to 200 C, you're having structural changes occurring. Also, these organic groups, which are advantageous in this epoxidation reaction, basically will go away.